Hello, and welcome to the Spring Summit for the URI ELECOMP Capstone Design program. We are Team BLE Tstat, and we developed a Bluetooth low-energy thermostat adapter. The technical directors for our project are Evan Cornell and Jack Hank. Both are embedded software and controls engineers for Takeo Comfort Solutions. Our team consists of Johann Carl Mueller, a computer engineer, and two electrical engineers, Tyler Aceto and myself, Eric Burlow. Takeo Comfort Solutions is a third-generation, family-owned company based in Cranston, Rhode Island. They deal with high-efficiency fluid control systems. The motivation for our project deals with hydronic heating control. Most households have mechanical thermostats, which are basically temperature-controlled switches that are very inefficient and are becoming obsolete. Programmable thermostats are more energy efficient, have better user interface, and are the new standard in heating and air conditioning systems. However, these thermostats require an additional 24 volts wire for operation. Anybody looking to upgrade to a smart thermostat would need to run an additional third 24 volt wire from the unit to the thermostat. Our device eliminates the need for such a wire. The anticipated best outcome of our project involved developing the hardware and firmware needed to pass power from two existing thermostat wires to a smart thermostat and send a Bluetooth signal from a microcontroller to the control unit when the thermostat heating state changes. The hardware was demonstrated on a breadboard prototype, and the firmware was developed and shown to work on the NRF software development kit. Our fabricated PCB did have some issues with supplying power to the microcontroller, and our firmware failed to show on the NRF Connect phone application. Although the design concept for the device was achieved, some issues need to be resolved to get the prototype in working order. Our key technical accomplishments involved first researching and deciding on the right power management and isolation circuits needed for the design. We also selected the most cost and size-effective components, designed and tested the hardware circuits, and developed the services needed for BLE communication and wireless firmware updates. Smart thermostats are becoming the standard in household heating and air conditioning systems. With an increased demand in smart thermostats, there is a demand for easier installation and retrofit designs. The development of this device will increase Takeo's sales in the hydronic electronic control marketplace. Here is an overview of the project design. Our device deals with managing power to the microcontroller, isolating the thermostat heat call, and sending a Bluetooth signal to the control unit. Spice simulations were used to create a design concept. We decided on using a full bridge rectifier to rectify the AC voltage, a linear dropout regulator to step down the DC voltage, and an optocoupler to isolate the heat call signal from the thermostat. Our simulation results showed that the power management circuit was adequate for our design specifications, and the optocoupler was able to generate a DC pulse that could be configured in the firmware to send a signal to the control unit. Here is our breadboard prototype using mostly through-hole components. We used a load resistor to simulate the current that the microcontroller would draw during BLE communication. There's also a full bridge rectifier, the optocoupler and current limiting resistor, and the LDO with the input and output capacitors soldered directly to its pins. Our lab setup involved using an isolation transformer to safeguard against ground coupling and a variac transformer to dial in on specific voltages needed to test the hardware's performance. Now Tyler will talk about the PCB fabrication, the antenna layout, and housing design.
Thank you, Eric. Here we have our initial PCB design, which kept all of the components on the same side of the board for simplicity. However, this device is intended to fit inside of the wall, and thus the decision was made to mount components on both sides of the board in order to reduce the overall size. Here we have the updated design. As you can see, it's slimmer while still including all of the necessary components. On the front, we have the power management and heat call circuits as before, and on the back we have the microcontroller debug connect, and the Bluetooth antenna. as well as the addition of a new RF testing connector to ensure proper values within the antenna PI network. Here we have our heat call circuit. The full 24-volt heat call from the thermostat would damage the microcontroller if we directly connected the two, so we need to isolate it using an opto-isolator. The way that this circuit works is that the heat call passes through a rectifying diode and current-limiting resistor and powers the LED inside the opto-isolator. This in turn biases the phototransistor on the other side, opening a path and allowing current to flow from the 3.3-volt LDO output to the MCU pin. The MCU detects voltage on that pin and initiates a Bluetooth heat call to the control box on the heating system. In this way, the unit is able to receive the heat call without directly exposing it to high voltages and causing damage. The Bluetooth transmitter consists of two parts, the antenna and the PI network. In order to function properly, antennas need to be matched to a certain impedance, and the PI network can be populated with components of different values in order to achieve that impedance. The end of the antenna also contains an unpopulated resistor network. In this way, either path can be populated to connect to either the Bluetooth antenna or the RF testing connector, depending on what you need at the time. The second part of the transmitter is the Bluetooth antenna itself. For our purposes, an inverted F antenna, or IFA for short, was chosen for its low cost and profile. In order to prevent external damage, we designed a simple box to house the device, with holes on each end to connect the wires through. I'll now hand things off to Johan to discuss the firmware.
Thank you, Tyler. For this project, we had the job to choose a microcontroller capable of BLE connection, compatible with Teiko's libraries, and in accordance with our budget limitation. Since Teiko's other point of communication is using a Nordic controller, it would be easier to make it compatible if we choose a Nordic controller as well. After making a list with all Nordic controllers capable of BLE connection, we compared specifications and price. NRF 52805 was the cheapest and more compatible match. It has Bluetooth 5.2 supporting BLE, 64 MHz M4 ARM Cortex with 192 kilobytes of flash and 24 kilobytes of RAM. Here we can see a general flowchart of how the program will work. We have two threads, the main thread in the left where we keep connection to Teiko's central unit, and on the right we have a pseudo thread generated by a timer interrupt that will be reading the heat signal and updating that information on the main thread. Here we can see Sega Embedded Studio on the back and two terminal windows on the right. The up window is connected to the development kit via wire to receive info. The bottom window we use to generate the zip package to test the FU service. I'm going to download the firmware into the development kit, and we can see on terminal window connected through wire that the firmware started in version 1. Now the left we can see the image captured from an Android phone running NRF Connect. We scan for BLE devices and connect to T-Stat or device. And now we can see both services and its characteristics. Next, we are going to select DFU and select the zip package to demonstrate how to update the firmware over Bluetooth. I select the file and it loads into the bootloader. After it finishes, we can see on terminal window that now the service is on its version 2 and already connected. Here is the development kit, and I'm going to switch back and forth the signal on pin 12, where we are detecting the heat signal. From ground low to VDD high to simulate the change in signal, and we can observe on NRF Connect the value being transmitted and updated automatically as I change the wire. Because the signal analysis is verified over 8 consecutive bits, when the wire is disconnected from ground or VDD, whatever information captured in between might be enough to change the value, and that is why we can have the sensation that the videos are not well synchronized. But on the real device, we won't have periods with noise in the wire. It will have steady high signal when no heat call, and an oscillating square wave signal high-low of about 60 Hz when it receives a heat call. We can also request a read to get the current information. We would like to give special thanks to our 3 technical directors, Evan Cornell, Jack Kang, and Robert Kelliker, for always being available to answer our questions. And of course, thanks to our consulting technical director, Mike Smith, and our project coordinator, Dr. Sunak, for everything they do for the Capstone program.